Okay, what's up everyone? Today we're talking about isometries and unitary operators and some matrix factorizations involving these different types of operators. So, first off, isometries. We've encountered a number of isometries so far, and they're an important enough thing to give a name to. So, isometries are just linear maps between inner product spaces, or really between norm spaces, but we're doing everything with inner products here. So, they're maps between inner product spaces such that the norm of the image of a vector is the same as the norm of the vector. Notice these are potentially, at least if v and w are not the same, different norms. So this is a norm in w and this is a norm in v. Basically it says that they're norm preserving. It says that the image of something has the same norm as the original thing. So here's a fact. So note this. Suppose SV is equal to 0. Then, watch this, the norm of V, well, that's going to be equal to the norm of SV, which is equal to 0. So, V is equal to 0. That is, the null space of S is trivial, and S is injective. So all isometries are injective. A pretty cool fact. Isometries are nice. They work well. So let's characterize isometries. I'll give you a big old laundry list type theorem. Here's the idea. We're going to show a bunch of different facts about isometries. First off, we'll take S to be an isometry. We'll show that that implies that S adjoint S is equal to the identity. That is basically the... Well, so in the case that S is an operator, its inverse is its adjoint. Okay, cool. Then we'll show that, so some facts about inner products. We'll show that orthonormal lists are sent to orthonormal lists. And then we'll show a fact about the matrix of an isometry with respect to some orthonormal bases. So let's go for it. All right, proof. First off, for A implies B, which I will scroll up to. Ooh. Okay, which I will scroll up to now. So A, we're going to say S is an isometry, and then we're going to show that S adjoint S is equal to the identity. So notice this. If V is in V, then, okay, here's what I'm going to do. I'm going to take I minus S star S. I'm going to show that this thing is 0 by taking the inner product of it applied to V with V, and noticing that I can turn this into, well, check this out, VV, inner product, minus S star S, V, V. Okay. Now from this, I'll get VV minus taking the adjoint to the other side, I'll get SV, SV. Oh, can you see where this is going? This is the norm of V squared minus the norm of SV squared, which is equal to 0 since S is an isometry. So, I minus S star S is the 0 operator. That is, got my microphone in the wrong spot. Sorry, I'm adjusting it. Okay, that is S star S is equal to the identity. Okay, why is this the 0 operator? So here, just to clarify that point. Oof. Since I minus S star S is self-adjoint and satisfies I minus S star SVV. Putting my parentheses in the wrong place. All right, there you go. Inner product there equals 0 for all v in v. That is, we showed this last time, I believe, or yeah, last time I think, maybe the time before, but pretty sure it was last time. We showed that for self-adjoint operators, if the inner product of the image of something with that original thing is 0 for all things, then that self-adjoint operator is the 0 operator. So there we go, bada boom. All right, we got it. Now let's do B implies C. Let's show that if S star S is the identity, then SU S inner product SV is equal to the inner product of U and V for all U and V and V. Okay, so let's do B implies C. All right, so suppose S star S equals the identity. Then here's what we're going to do. SU SV is equal to S star SU V. Just pulling that S in the second argument back to the first one using an adjoint. And hey, wouldn't you know it, that's just U inner product V. Oh, we did it. Okay. Now let's do C implies D. Okay, C implies D. Okay, watch this. So we're assuming that SU inner product SV is equal to the inner product of U with V for all U, V, and V. Now, what we're going to show is that SE1 through SEN is an orthonormal list in W whenever E1 through EN is an orthonormal basis of V. Okay, so if E1 through EN is an ONB, well, let me make sure. Yeah, orthonormal basis of V, and SU SV equals UV for all U and V, then watch this, SEI SEJ inner product is equal to the inner product of EI EJ, which is equal to 1 if I is equal to J, and 0 if I is not equal to J. Oh, so this is exactly what we need to say that SE1 through SEN is an orthonormal list in W. Since, after all, they are orthogonal, pairwise, and they have norm 1. Since their squared norm is 1, their norm is 1. Bada boom. Okay, we got an orthonormal list. Now we're going to suppose that SE1 through SEN is an orthonormal list in W for any orthonormal basis E1 through EN of V. And we're going to show that the columns of the matrix of S with respect to the orthonormal basis E1 through EN and any orthonormal basis F1 through FM of W will show that the columns of this guy form an orthonormal list with respect to the Euclidean inner product. So let's show it. This one is perhaps the more involved in some sense, not that it's terribly difficult, but let's just do it. So D implies E. Okay. So let's let A be the matrix of S with respect to these bases. Then for K and R in 1 through N, we have that the sum from J equals 1 through N of A, J, K, A, J, R bar is equal to, okay, here, I'll write it out, then we'll talk about it really quick. All right, all I'm doing is I'm doing the sum of from J equals 1 to M of A, J, K, F, J. Here, let me write it, then I'll run you through it. with the sum from j equals 1 through m of a j r f j. My commas in here, I guess. Okay, inner product, which is equal to SEK SER, inner product, which is 1 if k is equal to r, 0 if k is not equal to r. Okay, let me run you through it. So, check this out. All I'm doing right now is I am taking this nice inner product. Basically, I don't want to throw anything off by being too pedantic about this calculation. The gist of it is just that, hey, all we're trying to do is show that this matrix has columns that are orthonormal with respect to the Euclidean inner product. So let's take the Euclidean inner product of two columns. Column 1 will be the kth column. Column 2 will be the rth column. And when I take their inner product, I am just going to, here, basically what I'm writing is that this is a dot k dot product with a dot r. So the kth column and the rth column dot producted together works exactly like this. This is the definition of it. I'm only conjugating in case this is complex. Nothing terrible. And all that happens is I'm going to go on through, bada boom, and now all I got to do is rewrite this in terms of what is going on. So when I go on through right here, what are the entries in the column defined to do? Well, all they do is they tell you how to write the image of the element ER as a linear combination of F1 through FM and so on. So there you go. And this just is exactly what you're going to do. You're going to take EK and ER, yeah? So you get 1 or 0, just because, as we're assuming from part D, that SEI and SEJ have an inner product that is 1 if I is equal to j and 0 if it's not. It's exactly the same thing I wrote right here. So this is from part D. And basically, if you go backwards, you can see that these guys will just be written as linear combinations of AJK, AJR. But if you start to split this off just by doing the bars, like the confusing step is maybe right here if you're not seeing it. All I'm going to do is I'm going to split this sum up into a lot of pieces. So here, let me write it out. If you sum here from j equals 1 to m, you'll get a jk, inner product f j, next entry, j equals 1 to m, a j r f j. And now, like that's from this piece, and this thing here, notice, is equal to the sum from j equals 1 to m of now pulling out this AJR, and you have to take a bar of it. So I've got my AJK, and now I've got my, I'll sum here just to be clear. J equals 1 through m yet again, and I'll get my AJR bar, inner product f j f. I should be using a different index variable right here. Sorry. These are both j's, but to be clear, when I'm pulling it apart like this, I should keep track of my index variable a little bit better. Let me call these like i's or something. Just trying to make it clear what's going on a little bit more. Just to be super, super clear so no one gets thrown off by the sum variables being the same. I mean, it's not like technically wrong, but it will just look really confusing if I don't do this. Maybe that's why this looked bad at first. Okay, there we go. And see, as you can see, these ones will be 0 unless I is equal to j. And so that knocks off all of them except for the case where I is equal to j, and then you get back this piece right here. Does everyone see that? Hopefully. Okay, so if you see that, then look, you're just taking the dot product. Bada bam. Nothing bad about that at all. Okay, cool. So D implies E. Now for E implies A, this part is not bad. It just may be a little bit long. So let's go, and I'll start on a new page right here, just to make sure we have enough room. So proof, I will say continued. Okay. Now for E implies A, all we have to do is start by saying, hey, if the columns of the matrix of S are an orthonormal list, let me zoom out a teeny tiny bit, in FM, then SE1 all the way down through SEN is an orthonormal list in W. Okay, so for V in V, notice that V is equal to V E1 plus all the way down through V En, where E1 through En is our orthonormal basis. This is our nice little formula, how to get the coefficients out of inner products for an orthonormal basis. Okay, cool. And watch this, SV is equal to, well, I'll just apply S to everything here. I'll get VE1, that coefficient, SE1 plus all the way down through VEN, SEN. Okay, so watch this, the norm of V squared. We all know what this is going to be. It's going to be the magnitude of VE1 inner product squared plus magnitude VEN. Oh, terrible EN there. Okay, magnitude squared. And the norm of SV squared is going to be, well, it looks like it'll be the same thing, right? After all, SE1 through SEN, these guys are all orthonormal, right? So I will just by orthogonality get that this is equal to VE1 squared, and then norm of this thing, but by normality, that's just 1. So all the way down through norm VEN, inner product, squared, and S is an isometry. Nice. Okay. After all, the squared norm of V is the same as the squared norm of SV. And since both of these guys are non-negative, it means that the norm of V is the norm of SV. Nice. Okay. So isometries. Maybe it seems a little bit complicated at first, but all it says is that it's norm preserving. The big things to take away from this theorem, this long characterization, is that being a norm preserving map means that in the case that you are an operator, that your inverse is your adjoint, that the inner product, and this holds whether or not you're an operator, that the inner product of images is just the inner product of the things you were plugging in, that orthonormal lists are preserved, and that the columns of your matrices with respect to orthonormal bases are themselves orthonormal. Okay, cool. Basically, it just says that isometries play really nice with orthonormal lists and orthonormal bases. Essentially, you can just kind of disregard the isometry and just say, hey, look, anytime I apply it, my property is preserved. Let's keep going, and let's do a little bit more and talk about a particular class of isometry that is very useful to use in practice. Okay, one very useful class of isometries are the unitary operators. So a unitary operator is an operator, not just a linear map, but a linear map from a vector space to itself that is an invertible isometry. So notice, when do you have this? Well, let's just think about it really quick. Let's go back. So all isometries have trivial null space and are injective. So if an isometry goes between vector spaces of the same dimension, injectivity implies surjectivity for linear maps between spaces of the same dimension, right? Oh, okay, cool. So operators that are isometries are unitary. Let's prove a bunch of facts about unitary operators. So if S is a linear operator, is an operator, a linear map from V to V, and E1 through En is an orthonormal basis of V, the following statements are equivalent. First off, S is a unitary operator. S star S is equal to SS star is the identity. S is invertible, and S inverse is S star. Notice, just from B and A right here, that S star S is the identity, is equivalent to S as a unitary operator, kind of picks up the point that I just made right there. Isometries always satisfy S star S as the identity. So this is equivalent here to being an isometry, which in that case means that all isometries between a vector space and itself are indeed unitary. Cool. Okay. Now this is of course provided that V is equipped with the same inner product. If you took a linear map from V to V, but where V has different inner products, then you would have to be a little bit careful. When we write S is an LV in this case, what we mean is S is a linear map from V to V as when we're talking about being a unitary operator, remember this involves being an isometry, and that involves the norm, which is induced by the inner product. So we're implicitly taking V to have the same inner product both in the domain and the codomain. So just to be careful there. I don't want anyone to make any mistakes on that. But then from there, we're going to say, hey, look, S is invertible and its inverse is equal to S star. I would say that B and C's equivalence is extremely clear. Then we'll show that that's the same as the fact that the image of an orthonormal basis is indeed, yet again, an orthonormal basis, that the rows of the matrix of S with respect to the orthonormal basis E1 through En form yet again an orthonormal basis in Fn with respect to the Euclidean inner product, and that S star is also a unitary operator, which makes sense since after all, S adjoint, S star, is the inverse of S. All right, let's roll through it. So this one's actually easier than the last one since we've already proved most of it. So for A implies B, let's do it. All right. If S is unitary, it is an isometry. So S star S is equal to the identity. Since unitary operators are invertible, this gives, check it out. All right, S star, well, that's certainly equal to S star times S inverse, since that's just the identity. But hey, check it out. S star S is the identity. So this is just S inverse. Oh, well, that's pretty cool. Nice. So we can say S star S equals S star, and both of those are the identity. Since after all, S star is the inverse of S. S's adjoint is its own inverse. Okay, cool. So let's do B implies C. Now, okay, B says that, so we're going to suppose S star S is equal to S star, and that's the identity. Okay. I think that this one's relatively obvious. All we have to show is that S is invertible. Okay. So by definition, S inverse is S star. That is what it means to be an inverse. If you do it on the left and you do it on the right, you get the identity. Okay, let's do C implies D. Okay, this one's not going to be too terrible. So C implies D. Since S inverse is equal to S star, implies S star S is equal to the identity, the previous result, the one we just proved, right and bad, delivers this via the equivalence of B with D in the last result. That is, going back to the last result, B says that S star S is equal to the identity is equivalent to SE1 through SEN being an orthonormal list in W for any orthonormal basis E1 through En of V. This says, hey, look, since S inverse is S star, then certainly S star S is the identity, which tells us that S applied to any orthonormal basis is yet again an orthonormal list, but this orthonormal list right here is the length of a basis. Oh, so it's an orthonormal basis. Nice. Now let's do D implies E. Okay. D implies E. So this will basically follow exactly from what we've done before. So to get to D implies E and so on, we just get, well, here, let's just roll through it. So D implies E. To be pithy, I'll just say this is a direct consequence of the last result, particularly D implies E there. Okay, so in the last result, we said, hey, look, if SE1 through En is an orthonormal list in W, then the rows of the matrix of S form an orthonormal basis of Fm with respect to the Euclidean inner product. Nothing fancy going on there. Easy. Okay, so bada boom. D implies E. E implies F. Nothing horrible here either. Basically, all of the rest of these are just apply the last one. Okay, so E implies F. So we'll say the matrix has has its columns and orthonormal basis implies that the matrix of S star, which is equal to the matrix of S conjugate transpose, does 2. Okay. So S star is an isometry, and given both the rows and columns of MS are ONBs, orthonormal bases, S star is invertible. Okay. So for F implies A, here, let me go through the last one and say a little bit more. Basically, maybe I've actually, I should say this in more detail. So for E implies F, we'll say the rows of this are an orthonormal basis in Fn with respect to the Euclidean inner product. So I should say rows here. So it says that, oh, look, S star, the matrix of S's adjoint, well, that's the conjugate transpose of the matrix of S. Here, let me be clear. I think I've just conflated rows and columns. I knew there was something wrong when I wrote that. It's going too quick. Okay, thanks. So this says that the matrix of S star has its columns an orthonormal basis. So S star is an isometry, and given that both the rows and the columns of the matrix of S are an orthonormal basis, S star is invertible. Well, okay, so having this be an orthonormal basis certainly implies that this one has columns an orthonormal basis, right? Then I should say doing the reverse gives that both these guys have rows and columns that are orthonormal bases. Just say with S star replacing S. That's how you get that both of these have rows and columns that are orthonormal bases. So S star is invertible, hence S is invertible. Bada boom. Now we have E implies F. Okay. That is S star is unitary. Yeah. Okay, so F implies A is easy. All we have to do is just do A implies F, which we've already shown, to S star to get S star star, which is S, is invertible. Or more specifically, I should say, is unitary. After all, that's really all we need to show is the invertibility. But since A implies, so unitary implies that adjoint is unitary. So unitary starting with the adjoint implies that the adjoint of the adjoint, which is the original map, is also unitary. Bada boom. So we just do A implies F with starting with S star to get F implies A. Okay, kind of a weird little trick right there, but fun nonetheless. And we've got this long characterization of unitary operators that essentially just mirrors exactly our characterization of isometries, restricted to the case where W is equal to V. In many ways, you could just replace the proof that we wrote here with do the last one, but replace W with V. All right, nice. So let's go a little bit further. Let's do some more stuff now that we got these boring long characterizations out of the way. All right, nice facts about unitary operators. So first off, we'll show that if lambda is an eigenvalue of a unitary operator, then its modulus is equal to 1. Proof. This is easy compared to these long laundry list many equivalences we've been doing. So suppose S is unitary and SV is lambda V for V not equal to 0 and lambda in the field. Then the norm of SV is equal to the norm of lambda V, which is the modulus of lambda times the norm of V. So, since S is unitary, SV in norm is equal to the norm of V, and dividing, the modulus of lambda is thus equal to 1. Just take over here and divide by norm V. To get 1 is equal to modulus lambda. I'll even say this all at once here in a nicer, clearer way. There we go. This is a cleaner way of writing it. So we just went and showed that 1 is equal to the modulus of lambda since the norm of SV is the same as the norm of V. Okay, bada boom. Not bad at all. Okay. So in the complex case, here's what we get. So if the field is complex and S is a unitary operator, Then there's an orthonormal basis of V consisting of eigenvectors of S whose corresponding eigenvalues all have modulus 1. And the same in the reverse. If you have an orthonormal basis of V consisting of eigenvectors of S whose corresponding eigenvalues all have absolute value 1, modulus 1, then S is unitary. So let's run through this. This is not a bad proof at all. So suppose S is unitary. Then S star S is certainly equal to the identity, which is equal to S star. Oh, okay. So S is normal. Thus, by the complex spectral theorem, there exists a basis, or I should even say, I'll even say, just to be more clear, there's an orthonormal basis. Oops. What is going on? Oh, my color selector got messed up somehow. There exists an orthonormal basis of eigen